Hello, welcome to my prequel video to Eigenstuff, which is going to be a series of videos explaining words beginning with eigen. So next video, we're going to explain eigenvectors and eigenvalues. But before we do that, this is just a little video to explain some basic notions of linear algebra that maybe people don't know, like linear independence of vectors, bases, spanning, and just we'll introduce briefly the notion of a vector space. So here we go. I'm going to assume throughout this video and probably the entire series that you kind of have an idea of how to work with matrices and vectors. Most people have seen matrices and vectors before, at least in some capacity. Maybe you've used them to solve a system of linear equations like 3x plus 7y equals 9 and 5x plus 6y equals 0. Sorry for the bad handwriting, by the way. And you've used a matrix. You've written this system of linear equations as a matrix equation, ax equals b. And then you've used something like Gaussian elimination to solve this system of linear equations with like an augmented matrix or something. You'll find when you try to do this, when you try to solve systems of linear equations with matrices, it matters what number system you work over, right? So all of these are integer coefficients. All of these coefficients to these equations are integers, but of course this system of linear equations, at least doesn't look like it, is not going to have an integer solution. You're going to have to move to the rational numbers if you want to solve this system of linear equations. So I'm going to really quickly touch on the notion of a field, which is what you need in order to be able to do linear algebra, like row operations. If you wanted to solve this by, rewriting it using row operations as an equivalent system of linear equations, you need to be able to divide by numbers, basically, like, you need to be able to take 1/3 or 1/17 or whatever of a row and add it to another row if you want to be able to connect similar systems of linear equations or equivalent systems. And in order to do that, you need to be able to use coefficients that come from a field. So a field basically is a set of numbers that you can add together and multiply together. So there's two operations in a field. And the main thing that distinguishes a field from other algebraic objects, for instance, rings, is that there are multiplicative and additive inverses for every element. So this is the important bit, is that you can take the inverse of everything in a field. There are some other field axioms that you've got to satisfy, like associativity and commutativity and whatever, identities and stuff. But mainly you just need to know that a field is a place where you can add and multiply numbers. And we're going to use a field to study what a vector space over a field is. So a vector space is the algebraic object that serves as the venue for pretty much everything in linear algebra, at least everything that you learn in just a basic linear algebra class. And a vector space is a place where you can add vectors to one another and scalar multiply them by numbers in a field. So if you have some vectors that can be added together and scaled, and you stay in the space, so both of these, if you add two vectors, you're going to end up back in the vector space. And if you scale two vectors, you're going to end up back in the vector space. If you've got those two things, then we call this a vector space over the field F. So lambda, the field of scalars, lambda comes from F. So that's another reason the field is helpful for us. That's really all you need to understand about our vector space, is the place where vectors live that you can add and scalar multiply. Of course, again, there's some more axioms that a vector space has to satisfy. Again, a vector space is a very special category of objects compared to the more general category of like a module. And a vector space is nice for a variety of reasons. You know, usually vector spaces are much nicer than a general module. And one of the reasons they're so nice is because they have something called a basis. And a basis for a vector space is something kind of a minimal set of elements that you can describe the entire vector space with. So we'll go over a couple of concepts, linear independence and span, of vectors in a vector space that will tell us what a basis is. And this is also in pursuit of later when we're going to talk about an eigenbasis. So a basis consisting of eigenvectors. So first, we need to talk about linear independence of vectors. Linear independence is really simple for, two vectors or something. If you have a vector v1 and another vector v2, they're linearly independent if you can't write v1 equals some sort of lambda times v2. If you can't do this, then v1 and v2 are linearly independent. So they're not scalar multiples of each other. They don't sit on the same line. Like, let's say this is R2, a two-dimensional vector space. By the way, we're going to almost exclusively for this first two videos focus on finite dimensional vector spaces. We'll get to infinite dimensional and nastier ones later. So these two vectors, they lie on the same line. Let's say this is R2, the plane. These are not linearly independent, but these vectors, this one and this one, those are linearly independent vectors. For any number of vectors, an equivalent condition to this is that a set of vectors is linearly independent if whenever you write a linear combination of them and it equals 0, that happens if and only if all of the coefficients are 0. So this is just a somewhat easier way so that you can compute whether or not vectors are linearly independent. To basically state that a set of vectors is linearly independent if no one of them is a linear combination of the other ones. Here's an example in R3. By the way, I'll use R3 a lot, R2 and R3. Those are vector spaces over R. Maybe we should have done some examples of vector spaces. The most common example of a vector space that you'll see is Rn. So that's the n-dimensional vector space, or n-dimensional Euclidean space. And it's an n-dimensional vector space over the real numbers. So all the scalars, you can scale these vectors by real numbers. And R, of course, is an ordered field. So these ones are linearly independent. These ones are linearly dependent because this one is a scalar multiple of this one, whereas this one is not a scalar multiple of this one. So this is a linearly independent set of vectors. All right, spanning is another concept we need. A set of vectors is said to span a subspace if for any vector that we can write in the subspace, we can write it as a linear combination of vectors from v1 to vn. So this set of n vectors would maybe span a subspace of dimension n or maybe less than n. Let's do an example from, or I have an example later, so we'll do that. The maximum set of vectors that can be written as a linear combination of any set of vectors is called the span of that set of vectors. Here's an example of span, and it'll also be an example of linear independence. So we want to calculate the span of these two vectors, 1, 1, 2, and 1, minus 1, 0. And these are two vectors in R3. So that's three-dimensional Euclidean space. It's a three-dimensional vector space over the real numbers. The span is the maximal set that can be reached by linear combinations of these two vectors. So another way to write that is that if we have two scalars, a and b, times these two vectors, where our scalars come from the field R, the set of linear combinations of them, where a and b run through all of R, that's called the span of these two vectors. And of course, this is, you can't see that, this is a subspace of R3. Let me move my face. There we go. Subspace of R3. That's what that says. So this is a nice one because we can draw a picture of it. There's R3. Here is the subspace spanned by those two vectors. So here's the vector 1, -1. Here's the vector 1, -1, 0. There's that vector. And then here's the vector 1, 1, 2. And there's two vectors, so they determine a plane. That entire plane is the span of those two vectors. Because if we take any vector on this plane, maybe this vector, we can write a linear combination of these two vectors. So like maybe it's -1 times this vector, and then 2 times this vector or something, right? We can write a linear combination of these vectors to get to any vector on that plane. We can also notice that these vectors are linearly independent because they're not scalar multiples of one another, right? There's no number that you can multiply this by to get this. So they're linearly independent. Another thing I should mention is that if you have a set of n vectors, they may not span a subspace of dimension n. They can span any subspace from 0 dimensions, if all of them are the 0 vector, to 1 dimension. Maybe they're all scalar multiples of one another, or anything up to n. So you can have any number of dimensions of subspace that are spanned by various numbers of vectors. Also, exercise for the watcher, find the equation, the Cartesian equation for this plane. I'll put it on the next slide. So now that we have the concepts of linear independence and spanning, we have the concept of basis, because a basis for a subspace of a vector space is just a set of vectors which spans that set and is linearly independent. So basically, the fact that it spans S means that any vector in that subspace can be written as a linear combination of vectors from the basis. And the fact that it's linearly independent basically means that it's the minimal number of vectors that can do that. So let's say that in R2, if we want a basis for R2, here's the plane, a set of 3 vectors cannot be a basis for R2, right? Because we might have this vector, and this vector, and this vector, and we want to get a basis out of them. So we could put this one and this one in the basis, but at that point we can already express this one as -1 times this red one here. So we don't need it in the basis, because these two would not be linearly independent. So a basis is kind of the minimal set of vectors that can be used to write every vector in the subspace. Sometimes people will talk about an orthonormal basis. That's when the dot product, basically, of all of your vectors is 0. So, the standard basis for R3, which is like 1, 0, 0, 0, 1, 0, 0, 0, 1. An orthonormal basis is something that's like this, where all of your vectors are magnitude 1, and they're all orthogonal to one another. So the dot product is 0. We don't really need an orthonormal basis. That's kind of nice to work with. So we'll often use the standard basis, especially for Euclidean spaces. All right, so here's the plane again. If we go back, we can notice that both of these satisfy the equation z equals x plus y. So since these two vectors are linearly independent and they're both on that plane, they span that plane. So let's look at that plane. By the way, this little t is just a fancy way for me to write transpose so that I don't have to take up too much vertical space. So the span of these two vectors, this vector and this vector, is this whole plane, and they're linearly independent. One easy way that we can check that they're linearly independent is that, in fact, these two vectors are orthogonal. Their dot product is 0. You can check that. But since they're linearly independent and they span that plane, they're a basis for the plane. So that means that any vector on the plane can be written as a linear combination of them, which we've already seen, and also that that's the smallest number of vectors that can be used to write that plane. When you have a vector space that is n-dimensional, meaning that there are n vectors in the basis, obviously the smallest basis that you can have consists of n vectors. And then just to see that we can in fact write any vector of the form x, y, x plus y, just an arbitrary vector on the plane, z equals x plus y, we can actually write it as a linear combination of 1, 1, 2, and 1 minus 1, 0. You can check that this is true. Okay, so one more thing about bases. Obviously, a basis isn't going to be unique. We can choose a whole bunch of different bases for any given vector space. There are some bases that are nicer than others for various things. The standard basis on R2 or R3 or Rn or whatever is often a really nice basis because it's orthonormal. But if we're talking about a linear transformation, as we will in the next video, we might want to change to a different basis that's nice for that particular linear transformation. And we're going to visualize what happens to the grid lines. So the grid lines on a vector space, especially in Cartesian space, we can imagine drawing the basis vectors. So if this is R2 with the standard basis, we can draw 1, 0, and 0, 1, and then just keep drawing them over and over. And that sort of gives us a coordinate grid. And so I'll use drawing those grid lines as sort of a representation of the basis that we're using for that vector space. So the standard grid lines you always see are, 1 unit up, 1 unit sideways. But we can change the basis to express vectors in terms of a different basis, right? We just saw that we could pick a different basis for R2, like maybe this vector and this vector. Those are some vectors that aren't orthogonal, but they are linearly independent, and we could express every vector in R2 as a linear combination of those. So we could use these vectors and just draw coordinates based on those. And we'll do that next time. And we'll use linear transformations to see how the grid lines change when we apply a linear transformation. Okay, bye.